All right. Hi, everybody. Happy Tuesday. Thank you for coming. It feels darker in this classroom today, maybe because of that. So some announcements. Just remember, homework 1 is due on Thursday. And remember, this is the class where I'm not allowing late work, so make sure to do it early. That way you can just turn it in when you're done if something happens. You can either turn it in soft copy on Canvas, or if you've done something on paper, you can either turn it in during class or anytime on Thursday. In my office in 103A, there's like a little plastic box outside my door. So you can just stick it in there, and then I'll come in on Wednesday or days. I'll come in on Friday and grade it. So that's the plan. Did I see a hand up? Any questions? Great. Yeah. Hard copy or soft copy, either is acceptable. The homework 2 math packet is going to be due a week later. So hopefully you've gotten a good start on the things in class. And so until next Thursday to finish it. That's the goal. Homework 3, which is there and also on Canvas, is now available, and we'll start going through the material and you can start that. I'll let you know when that's due. I'm not sure yet. Okay. That's our plan. I've added the new unit onto Canvas. So the packet is here, the slides are here. I've got the homework 3 posted for whenever it's ready. And the chapter 2 packet you can also submit on Canvas if that's your preference. Okay, let's get started. All right, so we're going to go into this discussion of algorithm analysis. And this is where some of our math skills are going to be put to good use. There's a lot more detail in the textbook itself in chapter 2. I've gone back and forth with myself of deciding what are we actually going to cover. And I've decided I'm going to give you the overview, but we're going to kind of gloss over some things because not everybody in this class has had Calc 2. And Calc 2 is what gives us the skills to do a lot of the more math type things. So we'll talk about the really important stuff. And then as you go, if you want more information, I will refer you to the textbook. Okay, so in terms of what we'll talk about, first we'll talk about the RAM model of computation. We'll talk about big O and also big theta and big omega, which you may not have heard about before. We'll talk about growth rates and dominance, kind of how to do this math. We'll see some examples. I have summations and logarithms in the outline. Each of those are this is one of the things that I've decided to kind of gloss over. I'll show you the notation so that you can be aware of it and kind of how it works, but we won't go into too much detail with that. All right. So we're going to make up a machine. We're going to design this computer and we're going to call it a random access machine, which gives us this computational model. And it gives us this model where, let's just say that every simple operation is going to take one time step. So whether we're adding numbers or doing some arithmetic, or maybe assigning a variable with the equal sign, or if we've got an if statement or calling a method or calling something else in the code, all of that takes one time step. We're also going to assume that memory access takes one time step. If you've taken an operating systems class, you may know that that's not always true. So it's not always true that memory access or going to accessing the cache or actually going to the disk to get memory, it takes a variable amount of time. But here, we're just going to assume it takes one time step all across the board. The important thing here is we assume that loops and subroutines are not simple operations. And so this should feel familiar from Big O, right? Where one of the things you're taught in Big O is look at the loops and pretty much ignore everything else. This is kind of what we're doing, except we're trying to formalize it a little bit better. So loops and subroutines are not simple operations. So this model is going to count, our goal is to count the amount of steps taken and calculate the amount of time that it takes to complete operations. And this model is going to be machine independent. So it doesn't matter if I'm on this Mac or my Mac from like 2008 or the server that executes everything brilliantly fast. Machine independent, doesn't matter. It's also language independent, where it doesn't, some languages can be faster than others. And so it doesn't matter. We just look at what are the steps and how much time has it taken just in like generic time units. So we'll write this amount of steps as a function. We'll write it as a function in terms of n. N is the size of our input. And so we can write this function, something like you've seen in algebra or something, where we can have something like f of n equals 3n squared plus 100n plus 6. When you look at equations like this in either the textbook or elsewhere on the internet, you'll typically see it in terms of like f of n or g of n or some other letter, or capital T of n, T meaning time. So we're trying to quantify how long is this program going to take. So I think the first packet problem, which you can just discuss with your neighbors, is we've got this function. What sort of program do you think it would look like? Just like in general, what do you think we've got this crazy equation. Come up with like an outline for a program that has this function. Remember, like O(n) squared is nested for loops. So kind of think about that. What program could look like this? Go for it. 30 more seconds. All right, what do you think? Any ideas? Go for it.
That finding like duplicates in a list.
Finding duplicates in a list?
Yeah.
How so? Mm-hmm.
Second one iterates to the same list.
Mm-hmm. Yeah. Okay, so that gives us an n, the n squared. And so for us to have 3n squared, we would have to do that 3 times. Yeah. Other ideas? Mm-hmm. Mm-hmm. Yeah, yeah. So quadratic algorithms. Yeah, so that's the 3n squared bit. Any other ideas? We've also got a 100n in there. So what is that, just 104 loops? One after the other? I guess. Plus then after that, maybe just like 6 simple assignment operations, something like that. So just reminding you of this is kind of what this structure looks like, where we've got 3 sets of nested for loops or nested loops, 104 loops, and then 6 additional items. That's kind of where we get this crazy equation. Okay, so using this model of being able to say how much time something takes, it lets us simulate it with any input. So if we've got an algorithm in front of us, we can come up with numbers or some sort of input, depends on what the algorithm is doing. But if it's for finding duplicates, we can come up with, here's a list of 1, 1, 2, 3, 4, 5, or 2, 3, 4, 9, 9, 9, 9, right? We can come up with concrete examples and test our algorithm with it and see how long does it take. But the idea is we want to be able to generalize, where that's where the abstraction comes in. We want to see how does our algorithm work under any possible circumstances. We can come up with concrete examples, but we want to prove the general case. In particular, we're looking for 3 different aspects here. So the best case, so the minimum possible number of steps that our algorithm is going to take. The worst case, which is the maximum possible steps we're going to take. And the average case is the average of the two. So for finding duplicates, this would be like if we were looking for a duplicate in our list and it was the first 2 elements, then that's great. We didn't do any extra work to find the duplicates. So that would be the best case. The worst case would be what? Yeah, at the end of the list, or there's no duplicates at all. And so we've gone through all of the list and didn't find any. Oops, guess we did all that work for nothing. And the average case would probably be like it's somewhere in the middle. Make sense so far? Okay. So let's say you walk into a casino with N dollars. How much do you walk out? Talk in your groups. What do you think? What's the best case, the worst case, and the average case for walking out of the casino? While you do that, I'm gonna pull up a link.
Eventually you get that, right?
Okay, any thoughts? What's the best case? Double your money? Okay. Any other ideas for best case? Bankrupt the casino. So there's a multiplier for n, right? If you get c times n, where c is some constant, could be 2, could be however much money a casino has. You walk out with more money than you started with. What's the worst case? Lose all your money. So you can go from n down to 0, or maybe negative, which would be even worse. Average case? Break even. Walk out, or walk in with n dollars, walk out with n dollars. Sure. Yeah. Let's see. Nope, still can't see that. So the textbook has some, where's it? There it is. No, video, please go away. So the textbook has some discussion of like the actual probability of winning for some games. And so there, depending on like which games you decide to play, you have some chance of winning. And so this is the house edge. And so some games are like very much stacked against you. So if you chose those games, then your best, worst, average changes. So yeah, that's basically what I wanted to mention. So depending on the game, then it changes. So what we're going to be looking at is we're looking for something like this function where we have our algorithm and we know how many steps it's taken. Let's say we have this equation. We want to give it what are called bounds. So like we've got some number of steps and we've got the size of our input, the problem size in terms of n. And we want to look to bound it by these 3 items of the best case, the worst case, and the average case. So the worst case is going to be this upper bound, where this is the worst possible, the highest number of steps we could possibly take. The best case is the lower bound, so the least amount of steps we could possibly take, and the average is somewhere in the middle. Okay. So, right, so we have something like n as our input. That's typical. And if we want to say like what's the best, worst, or average case of something like this, the best way for this is to say it grows quadratically. If you remember the tricks from Big O, it's basically look at the biggest term, ignore the constant, and that's your O of whatever for this function. And those rules still apply. So you'll still be using those skills. We're just adding some rules to it. Okay, so here are two graphs that the textbook has. Let me zoom in on each one of them. So the goal is to find these functions for the upper and lower bound. Okay, that's the goal. And you may notice for something like this, so let's say we've got some upper bound, we've got some lower bound, but in the black, that's the actual function. And so you'll notice it like goes up over the upper bound and then it kind of still wobbles around, but stays within the upper and lower bound. So the idea is we will have these functions, but maybe the upper or lower bound property doesn't apply unless we're past some points on like some amount of n. So we typically call this n naught or n0 with 0 as the little subscript, which you can see right here. So these upper and lower bounds are valid past this number n0. So we want to find some value for which the upper and lower bound applies. Okay, let's look at the other one. And so this is what we're looking for. So A over here is O of n, where past some value, this upper bound in blue, C times G of n, the upper bound applies. For B, it's similar, so we're finding a point where after this, we know the behavior of the function, and so the lower bound is going to apply after these initial values. And similar for the average case, we're looking for an upper bound and a lower bound. And yeah, the average case is a little bit tricky. We'll talk about it. Let's see, anything else to mention here? The worst case is big O. The best case is big omega. And the average case is big theta. Okay. So now we're going to look at the math definitions, and it's going to hurt your brain a little bit. I'm sorry in advance. So up on the top this is the definition from the textbook, and then on the bottom is my rephrasing of it. So we say that O of G of n is worst case bound on f of n, when there exists a constant c such that c times G of n is an upper bound on f of n. So we're looking for some function G of n such that we can multiply it by a constant, and then the result of this function for every n that we plug in, it's going to be bigger than our original f of n function. So that's what we saw here. So for some way along the x-axis, we found a point where our function g of n, maybe multiplied by a constant, is going to be bigger than everything that f of n is going to give us. Okay, so my rephrasing is a function g of n is a worst case upper bound for f of n when we can choose a constant c, look at c times G of n, and pick values of n for where c times G of n is going to be bigger than f of n as n increases. That's upper bound. Anybody need more time? Okay. These slides are also on Canvas if you need them later. Okay, good to move on? All right, lower bound. So again, we're looking for a function g of n, and we call it this g of n big theta. The lower bound for when there exists some constant c, such that when we multiply c times the function we found, g of n, it's going to be less than every value of n we can plug in for the function f. So right before we were looking for, we can plug things in and it'll be greater. Here we're looking to plug things in and it'll be less. So that's giving us this middle one here, where it's giving us the lower bound. So yeah, so it's looking for a best case lower bound when we can choose some constant c. First, we need to find what g of n is. Then we choose some constant c, look at those multiplied together, and then pick values of n as n increases and say, is this going to be bigger than our original function? Once we found a function like that, then we say that that's a lower, g of n is a lower bound. Park here for a moment too. Anyone need more time? Okay, continuing. So the average case, similarly, we're looking for a function, which we call g of n. And we say that's big theta for some function f of n, where there's two constants, we'll call them c1 and c2, where if we multiply c1 times our function that we found, everything in that function is greater than the original. And then there's some other constant where everything, when we multiply the constant by our function, that's going to be less than the original function. So we're looking for one function that does both, where we can pick two different constants and we'll find the one gives us everything greater, the other gives us everything less. So that's this, where we've got two functions just with a constant applied. And the difference of constant gives us an upper bound and a lower bound. And so then we say that g of n, that's our big theta. Okay, so g of n is an average case bound for f. And that's when we can use the same function to find both an upper and lower bound. Something is only in big theta if it's both an upper and a lower bound. And the other thing that is interesting to mention, it doesn't only apply to big theta, it also applies to big O and big omega, is that these are actually sets, right? So if I've got a function n squared, there's infinitely many functions that are bigger than n squared and infinitely many functions that are smaller than n squared, right? I could draw those functions any way I want. These are actually sets where we're just trying to pick one that is an upper bound or lower bound or both, right? So there's going to be options. We're just looking to pick one of them. Here's another visualization where big O is we're looking for the upper bound after some point. Big omega is we're looking for the lower bound. and big theta is we're trying to target right in between. Okay, so the packet problem is what are the three of these? Let's do the first one, just so you kind of get the idea. And at first it's going to be a lot of guess and check. Okay. So let's look at it. I think I would like let me make a new slide. Where did Zoom go? Share this screen. Okay, so we're looking for big O, big omega, big theta. So let's first okay, first let's ask. Do we think n squared could be big O? Yeah, I mean that's what you've been taught, right? To just look at the first term here and then isolate the variable n squared and then throw away the rest of it. But let's look at it using our definition. So we've got n squared. And the question is there a constant and some beginning value such that everything after that is bigger? Let's actually open up Desmos. Open graphing calculator. And the function here is 3n squared minus 100n plus 6. And so you'll see it's one of those functions where we moved down a bunch. So the bottom of the parabola is down at 16 and negative 827. We don't really care about that. What we do care about is the things that are above 0. So we're looking at this part. And oh, that's not how we type n squared. Can we zoom out in a way that's helpful, please, Desmos? So initially, when you look at this y equals n squared versus our 3n squared, so first of all, it's kind of undefined up to some point for us. But if we go, let me zoom out for a bit. There's a point where they cross, right? So I think this might be the point where they actually cross. Somewhere around here. We're like around x equals 50, then it changes. So the question is, so for what value of c should we do? I don't know. We could choose we could choose 10 if we wanted. Yeah. 3. Yeah. Because 3 times n squared. Yeah. Because then we've got minus 100n plus 6. Yeah. The constant is just because we can scale up this function, right? So there's a difference between, let me not show that. So the difference between n squared, 2 of n, and 3 of n. So that helps us make the upper bound or lower bound. Let's see if y equals, if we've got like just a for loop that just goes for n, and we're trying to find the upper bound for this, y equals 2n is going to give us a bigger value for all values of n. So we can say 2 is our constant and our big O is O of n. This is mostly guess and check. If we want to look for a lower bound, maybe 0.5, and that gives us a lower bound on every value of n for n greater than 0. Okay, so back over here. Yeah. Your choice of constant matters. I mean, doesn't. Yeah, all we care about is that there is a constant. Okay, so if we said that n squared is our main function, g of n, and c could be what? 4 or 3. And then the question is, what is the value when this thing starts changing? So if someone wants to get out their calculator, try, so let's say 3n squared, and let's look at n of 50, 100, and 150. At which of these is 3n squared greater than this value? Yeah,
Oh, all of
all of them. Someone want to confirm that? Yeah. So let's try 0 and 1. Um, 3 times 0 is just going to give us 6, right? And 3n of 0 versus 0. Someone have these numbers for the first one? And what's 3 times 50 squared? 50 squared times 3.
about
Yeah, so if this is bigger, Well, not too bad that this is bigger too. So this means that, yeah, so anything greater than 0. So we found our n naught, and that's 1. Is it 1? Three minus 100 plus 6, yeah, it is 1. Yeah, so for n greater than or equal to 1, 3n squared is always going to be bigger than f of n. Because of that, because we've decided c, which is 3, and n naught, which is 1, the big O of this function is read as n squared. So we ignore the constant, and we just give the function which we call g of n. Is that clear so far? So we're looking for a function and a value of n where we can start growing and getting bigger. Okay, let me add another slide for, I wish I could. We could add a slide just directly in here. Kind of only. Okay. I'm showing the right thing. Yes, I am. Okay, so now, so we've decided big O is n squared. So the question is now, what's the lower bound? So first let's try, is n a lower bound? Probably, yeah. N is less than 3n, so it's after some value where this function is above 0, n is always going to be less than that. What about n squared? Could n squared be a lower bound? We've seen n squared where we give a constant and have some initial value where it's bigger. It's possible it could be less. Talk with your neighbors. What do you think? What's the question? Right. There's a certain point along the x-axis where everything to the right that our property upper or lower is going to hold. Yeah, so in that case, the constant, yeah, so the constant would just be 1.
Yeah.
And the n naught is just wherever it crosses. That may be the easiest way to start thinking about it. But C and the n naught can be whatever we want it to be. All right, any ideas? Could n squared be a lower bound? Yes. If so, what's C? And what's n naught? Could be anything. What do you think n naught is? Okay, so let's check it. So n squared, so for 0, this is, what is it? Negative, or no, it's just 6. For n equals 0, f of n is just 6, right? We plug in 0 for each of the n's. And so g of n, which is n squared, is 0. 6 is greater than or equal to 0, so we're good so far. Does this continue to hold as n increases? That's 3 minus 100 plus 6, which is 9 minus 100, which is and I think -91. My ability for mental math plummets when I stand up here and present something. And then for n equals 1, what does n squared give us? I mean, that's not the end of the world. Maybe n not equal 0 is not where we want to start. Anybody have any ideas for what we want n not to be? Otherwise, we keep, I mean, I think, yeah, 50? Let's check 50. Can someone plug into a calculator? 50 squared, 5 squared is 25. 1, 2, 3, 4 zeros? Wait, no. No, there's only 1 0, so. So plug in 50 for f of n. For f of n.
Oh, at the time was 22506.
Okay. So that's greater than or equal to. Great. And now the thing you would do is you would convince yourself, you look at 51 and ask, is this also going to hold for 51? And this can be helped by looking at the actual graph of the function of, if we go back to Desmos or your favorite graphing calculator, and let's look at n squared. And there's some point where they cross, and it looks like it's around 50. So after that, there we go. So 50 could be our n naught, 51, 52, 100 could also be our n naught. That's more than maybe it needs to be, but it's also acceptable. So 50 is our n naught. And our constant is 1 of just n squared. And so now we can say that the lower bound on f of n is n squared. So once we've found a constant and an n naught, then we ignore them, throw them away for now, because all we need to write down is that n squared is our lower bound. Okay, so we found a constant, we found an n naught. Those are our two keys. Are we good to move on? Question. G of n is n squared. I would also maybe argue that G of n could be n as well, right? Remember, this is a set. The big omega is a set of functions that are lower than f of n for some constant and for some value that we start counting after that, right? So n squared is one that we happen to figure out computing. N is probably also acceptable. So now we know that the big O of f is n squared, and the big omega is also n squared. Guess what? We've solved big theta now. Because remember, the definition is we're looking for some C1 and C2 such that we've got some function multiplied by that first constant past a certain point is going to be greater than our original function. And we're looking for some constant C2 times that same G of n, where everything past some points and not is going to be less than everything that f of n is going to give us. Have we done that? Yeah. Yeah. So because we know this and because we know this, we can say the big theta of f of n is equal to n squared. Because n squared, which is g of n, is in both the worst case and the best case. So that means we've bounded it on both sides. So the average case, the n squared also holds for the average case. So yeah, so this is where the average case can kind of help to restrict us a bit, where the worst case could be anything we want, the best case could be anything we want, but for the average case, we're looking for something that it's kind of in the middle. Yeah.
Format the answer, like how we have it up there, or what you want to like concept use.
I would probably, so right now, I think no specific format. I'm just looking for what's C and what's and not, and maybe a little bit, if you jot down a little bit of your reasoning for that, then I'll be happy with that. Okay, so let's give a shot at the other packet problems. We don't have to get through all of them, but I want to give you some time to just practice this. So let's go till maybe 240 or so and do as much of the other ones, which are 2 to the n plus 1, x squared plus y squared, which I'm just realizing is not in terms of n, so it should probably be f of x comma y. And then the last one, t of n, which is another n squared plus n plus log n thing. Okay, give it a shot. Work together. Talk with your table mates. Okay. Yeah, sure. That's a great place to start.
Of the C.
Okay. So you want to. Yep. Yeah. Given is the action, right? But yeah, this is very long. So then your C would be. So for the upper bound, 2, 3. And then your N naught is. Yeah. So then there was limit, then the upper bound is. Yeah. So then for the lower bound. It's like that. One. Not until. Your else terminated one, there we go. And then your average case is. You've got to go upper and lower bound. Yeah. Yeah. Double perfectly out. Yeah. That's fine. As long as there is a constant which has and not if it's property hold. So there's infinitely many options. You just have to choose one and tell me what.
And sorry. It's like.
It's just their.
One, and you're in
Just pick one, so like for the first one we did, we did four. See what we first are, like, some are long, right? Apparently it's going pretty good over there.
Get it?
Whatever one's the biggest one, and then you just do.
That's not. I mean, the lower bound might technically be that.
You get the,
I would encourage you, if you're having trouble getting started, try and just isolate the main part of the function. So like, when we were looking at the 3 of n squared, try looking at 3n squared. So if you can work with exponents for 2n plus 1, to get the important part out of that, something in terms of n by itself. Go for that. Okay. Yeah. Yeah.
Then what would be? What would technically be like that?
Okay, experts. Right, so there's a point along the x-axis where the property holds. I'll leave this up.
There was a skill issue.
That's not as wide.
Right, there are different points on different.
But I don't. I'm sure he felt good about it.
I looked at like everyone getting high, and then
Yes, right, I understand. You could add some, so these are like, you have to. The way that we express that is these are hard work. Yeah.
You know, maybe keep your tutor like quiet. For this room.
Yeah. Okay, that's the trick question answers. Right. Which function that is written? But what you're what if it was
You want to see on that, like order.
yeah.
I think.
Okay, let's look at 2 to the n plus 1. Do I have my? It's all the way at the end. Of course it is. Okay, so if we remember exponent rules, and when we're looking at 2 to the n plus 1, if we expand it out, what does that give us? Yeah. Yeah, 2 times 2 to the n. That's the case of the product rule, where since we've added 1, 2 to the 1 is just 2. And so when we have 2 to the 1 times 2 to the n, that gives us 2 to the n plus 1. We clear on that? Great. So this tells us that if we try and simplify the function that we're given a little bit, now we've got something 2 to the n. This is just a constant, so we can ignore it for now. And so this gives us a g of n to try for the second one. Okay, I'm going to flip through a bunch of slides and go back. Prepare yourself. Okay, so our candidate g of n is 2 to the n. The way we got there was knowing that 2 to the n plus 1 is 2 to the n times 2. And then we're like, throw away the constant, just look at the thing that's in terms of n. All right, this is our candidate. Does anybody have a C and an N naught for which this is the case? This is the upper bound. Yeah. C is 2, N naught is 1. Cool. Anybody else have something?
Is 4.
Anybody else have something? I know that a group over here had something slightly different. Yeah. So here's the thing. There's infinite values of C for where this works. And let me prove this to you. So let me get rid of all of these guys. And if I type y equals 3n, no, wait, we're not on 3n anymore. We're on 2 to the n. There we go. So that's our original, or let's see, our original function is 2 to the n plus 1. Not that kind of plus 1. Okay, that kind of plus 1. That's our original function. That's f of n. We just mapped 2 to the n. I think it's fairly clear that, whoa, no. That our 2 to the n is always going to be smaller, right? So 2 to the n is a candidate for the lower bound. And then someone said C is 2 or C is 4. So let's see, y equals 2 times 2 to the n. Wait, no, that's the same thing. Did I mess that up? I think the case where C is 2 would not be correct in this case. So let's try 3. 3 gives us an upper bound. We can see that. So for C is 3 and n is 0 even, n greater than 0, then the 3 times 2 of n is an upper bound. So for C equals 3 and n naught equals 0, g of n equals 2 to the n is upper bound for f of n. That's how I would write that in a sentence. Or we could say f of n, the way that they write this in the textbook is a little bit confusing. But we would write f of n equals O of, and then our g of n thing goes in here and we write 2 to the n. That's how we express that 2 to the n is an upper bound on f of n. And the thing is, there are infinitely many C and N naught. Like, we could take 500 and it zooms way out, but you can assume that once it crosses the y equals 0 points, it's going to be bigger than 2 to the n plus 1. Always. Similarly, if we fix it at 3, we could have chosen like any value of n for n naught, right? There's an infinite amount that we could choose from. So the point is to just choose one and say that, and then move on. Okay, so then for omega, in Desmos, we see that the constant here would be 1, right? So if for omega, our candidate g of n is, again, 2 to the n, and so then for c equals 1 and n naught equals 0, we can say this whole thing again, where instead of c equals 3, c is 1. And then we say is lower bound or f of n. So the way we write that is f of n is equal to big omega, and then inside we stick in 2 to the n. And so once we've got both of those, we have the same function that is both upper and lower bounds. Therefore, we've got our big theta. And so we can say f of n equals big theta. That's a weird looking n to n as well. All right, because we've shown upper and lower bounds. Once we do upper and lower bounds, then we get our big theta as well. So this is really the sort of information that I'd be looking for, like on the homework of here's my C, here's my N naught, and here's the G of N. Okay, we've got 20 minutes. There's a problem on the back of what are some questions that you have. Does anybody continue to have questions that they want to ask, or you could just write it down? Okay. That one's not really mandatory, just maybe space for notes. Let's talk about growth rates for a bit. So, let's consider f of n as 0.001 times n squared. And we could say g of n, where the constant is 1,000. So if we consider both of these as like independent functions. So one is 0.001 times n squared, another is 1,000 times n squared. The worst case on, I hope it is clear by now that the worst case on both of those is just n squared, right? Throw away the constant, we can find the some value of c, we can find some value of n naught, for which all n bigger than n naught are going to be bigger than each original function. So the big O of both of them is n squared. However, g of n is literally 1,000,000 times larger than f of n. They both have the same worst case upper bound. So this may be like a kind of sticking point of like what gives. They're growing at going to grow at different rates. This is a table in the textbook. I did my best to snap a picture of it. But it tells us that, so we've got different columns. The first column is n, the second column is log n, the third column is, the first column is n, which is the size of input, right? There's different numbers for 10, 20, 30, 40, 50, and then 100 all the way up to 1,000,000. And then in the past that column, we've got log n, we've got n log n squared, 2 to the n, and n factorial. So these are different classes of functions. And the point is to see how long will a log n function take for n equals 10? How long will an n log n function take for n equals to 100? And it's estimated about 0.644 microseconds, and so on. So, yeah, so some of the things we can see so far is that, like, for log n, even as it gets up to millions or billions, log n, it still takes like no time at all, right? Even for the highest value that's listed on the table, it's still 0.03 microseconds, which is really, really fast. For a function that takes n steps, for a billion, it would be 1 second, which is still, decent. Fair bit slower than the 0.03 microseconds, but a second's not a second. It's just a second, nothing to sneeze at. And n log n gives us about 30 seconds, still fairly good. For n squared, that's where we start to get into like the useless numbers of, if we've got an n squared algorithm and we've got a billion, our size of input is a billion, it's going to take us 30 years to get it done, which is probably not the greatest. And so on. So there's a certain, so for the 2 to the n and n factorial, it becomes really clear very quickly of how big the input can be before the algorithm becomes useless. So 2 to the n kind of maxes out at n equals 50, which gives us 13 days to compute something, because after that, it's a useless number of years spent computing something. And then n factorial is really only good up to 10 or so, because after that, it's, who wants to spend 77 years running some program? I don't. So yeah, so I hope that's interesting. And so the reason that it connects to, can I go back a slide? The reason it connects to this is that regardless of the constant in there, you can see the growth rate. So it'll grow similarly, regardless of the constant. So it's only the size of the input that matters here. So that's what allows us to kind of throw away the constant and just look at how big our input is. And this tells us how much our function is going to grow. Some insights from here. Additionally, all algorithms at n equals 10 take roughly the same amount of time. So n equals 10, 0, 0, 3, 0, 1, 0, 3, 3, 1, 1, 3. So they take roughly the same amount of time very quickly. Even if you go up to 20, the first 5 kind of still take around the same amount of time, but the last one certainly does not. N factorial is useless when n is greater than or equal to 20. 2 to the n is not good for n equals 40, which we see here. So 18 minutes is decent. 13 days is probably not. N squared is okay up to, what is that, 10,000? I don't know. I mean, depending on the algorithm, I think I have some fairly intensive algorithms that I've implemented, and it takes maybe like 2-3 hours to go through my whole data set. I'm okay with that. So it's just a matter of what are you trying to compute and are you comfortable with the execution time? Yeah, the O of log n is pretty much good forever and ever. So then we've got our classes of functions, which is one of the packet problems, just to write down what are they. And so, for example, so constant functions are the first class. This is basically as good as you can get. It executes and then it's done. Happens instantaneously, which, for example, is something like adding two numbers, which in our RAM model of computation, like if you add two numbers, the plus just takes one time step. So we're done. It's constant. It's not in terms of our input in any way. Print the Star Spangled Banner. If we know how long it is, we just print it. That's one thing. We're done. Find the minimum of n and 100. We're not going through n in any capacity. We're just finding what's the minimum of n and 100. Logarithmic functions. Sorry, that's kind of in the way there. Logarithmic functions look something like log n. And an example of that is binary search, which is where if I have a list or array of something sorted, then I look at the middle and or if let's say I'm looking for something, I start at the middle and ask, have I found it? And where is it in relation to what I'm looking for? So if it's less than, then go left, and then if it's greater than, go right. Linear functions, that should be an equal sign. Which is just a line, where an example for that is maybe we're looking at each item once in an n element array. And then, or maybe we're finding the biggest thing, or maybe we're finding the smallest thing, where, we're going through the array. And the worst case is we look at every single thing until we find what we're looking for. And then we've got superlinear functions, which is n times log n. So it kind of will angle up. Sublinear is log n. So that's where we're kind of leveling out at some point. Superlinear functions like n log n include quicksort and merge sort. And I think I will leave the rest of them for next time. So we'll pick up here.
Question.
Yeah.
So, the sublinear to here, it was kind of like synonymous with like, concave and convex.
Probably. I think so. That's what it looks like to me. Yeah. All right. Thank you. Remember, homework 1 is due on Thursday. No late submissions allowed. So make sure you get it in by Thursday. Thank you. I'll see you next time.